approximately. This is, as I said yesterday, this is all, you know, within hand-waving factors. This is good for government work. This is assuming perfect no loss of energy or anything like that. We then amplify the signal from the transducer, this larger amplitude that we've measured. We amplify that with in all of the cases, we amplify it with a superconducting, in all cases but one, we amplify with a squid amplifier, a Josephson junction amplifier, same thing, a superconducting amplifier, one that is relatively noise-free. Okay. Now, I'm give you some numbers here. This is, and I didn't give this to the class yesterday, only indirectly in the in some of the graphs that I showed. Their peak sensitivity in strain per root hertz is about 10 to the minus 21. Okay? The units, for those of, I guess everyone here is familiar with the kind of units that we're using, so that, you know, it's a little disconcerting to those of us that are simple plumbers that want a unit with everything that we're measuring, and the fact that strain is dimensionless makes it, you know, you end up with seconds at various places and nothing else, and it's hard to imagine what it is you're measuring. Anyway, so I put in the strain even though it isn't there. The crucial points here is that we've been able to run these detectors together for quite an extensive length of time. Now, I'm just to put things into, to sort of tie some things together. We have not been terribly good in our community about a consistent way to express things. Let me, so let me try to couple some things together. This is the H, the strain, if you will. I'm comparing an interferometer and a resonant detector here, obviously IFO and bar. And these were some numbers that Warren Johnson dashed out for Ray Weiss, and I just cribbed them from Warren. A way to compare to get the way that the spectral density, strain per root hertz, and the sampling time or the beat time, whatever you will, the sampling time compare in an interferometer and a resonant detector. The difference between those two things is that in an interferometer, we're generally considering the signal to be much broader than the bandwidth of the, in the bar detector, we're considering the signal to be much broader than the bandwidth of the detector. And so this is why such things as the bandwidth of the bar detector, the antenna, enters in down here. And in fact, I wanted to put this on for a particular purpose, that you can see here that you gain a great deal in your strain sensitivity if you can figure out a way to increase the bandwidth of the bar detector.
So this HM that you're writing down is the actual amplitude of a broadband signal?
Yes, yeah.
So this is the sensitivity. So if you were going after a narrowband signal, you would look a lot better with the bars.
Yeah,
right?
yeah. Yeah. But this is basically the equivalent noise. If you look at your detector and you say, okay, now what kind of, let's assume the detector is noiseless and the only thing that's exciting it is Gaussian gravity waves. How big is that H?
And your tau s, when you imagine this, is the tau s basically 1 over the frequency? Or?
It's your sampling time. It's the sampling time that the time between samples, assuming that you are sampling a signal at regular intervals, and
of course. We normally sample at much higher sampling rates than the gravity waves you're going after. So you're not wanting to use 20 kilohertz sampling.
No, I can't use 20 kilohertz sampling time because the response of my bar is not such that I can get anything from it. You guys can.
Well, no, not really.
Yeah.
Kilohertz is only sampled up.
Yeah, yeah.
And so the tau s we're to think of is something more roughly like the period of the gravity wave.
Yeah, yeah.
That's good.
Yes, sir.
So delta FA correspond to the Q
ba-
value FS
FA, yeah. This,
correspond to the Q value of the detector.
yeah. Not strictly, but this is a complicated question with respect to a bar detector, and let me explain why. Your answer is correct, but not completely correct. And the complication comes from from what we had earlier, from the fact that we have this beating of the signal between the transducer and the bar. The signal that we measure is this, all right, which is comprised of, hey Ron, which has two frequencies. We have the sum and difference frequency, and we're sensitive in both of those places. I believe I put that graph in this talk. We'll see. All right, I want to say some. This is a repeat of that previous slide, except that I wanted to give you two things. I wanted to give you a website to look at. This is for the IGEC, which we put together a couple of years ago. We have finally succeeded in getting all of the bar detectors in the world, getting all the people to talk to each other, and hopefully to express their data in some common format. That common format you can look at on this site. This is to illustrate one other thing. All of the bar detectors until our last run have all been oriented parallel to each other. The red line on this is the mark of a great circle on the surface of the Earth, the cutting of the surface of the Earth with a plane through the center. And they've all been oriented perpendicular to this great circle. And by being oriented perpendicular to the great circle, imagine that you have a sphere, then the bars are all parallel. And regardless of where they are on the surface of the Earth. And because they are all parallel, then the signal strength detected in any bar should be correlated. So in other words, if you see something in one bar somewhere in the world, you ought to see something approximately the same size in the other. And so there's no way to get around someone saying, oh, well, my detector was not behaving well. Well, they can always say my detector was not behaving well, but they can't say that we were pointed in some other direction we shouldn't, and so there was a signal there, but we just didn't see it. So these are the 5 resonant detectors in operation and have been in operation up to this time. And unfortunately, I mentioned this in the class yesterday. Unfortunately, this is a talk that I gave in Albuquerque, and Kip thought it might be appropriate for this group. So I was in the library, but the Fairchild Library. And I'm sorry, I just got...
Did you get introduced?
Yes, yeah. And so I talked to Kip's class yesterday, and for those that I talked to, this is a continuation for those who weren't there. Let me just say that I gave sort of a loose picture, I guess is probably the politest way to put it, of how a resonant gravity wave detector works. And so today, then I want to give you a little bit more up-to-date picture of just where things are and what I believe their status to be. And I cribbed a good bit of this talk from these people. So, oh, I can use my finger. My finger will work.
There was one here.
Ah.
That's lethal, so carefully.
Maybe I should use the other end. And then, so let's the detectors that I'm going to consider. These are the 5 working resonant detectors in the world today. And what I hope in the course of this talk to convince you of is that resonant detectors are working. They are pretty good. I didn't get into very much of that in my talk to Kip's class yesterday. They are pretty good at what they do, and they can be made better. And moreover, I think that for the next few years, with LIGO, Virgo, GEO, TAMA operating, I still think that the resonant detectors have a part to play. And so we will take, that's sort of just a statement of my prejudice. I've been working on these things for a long time, and you are perfectly free to disagree. However, if you disagree, you're wrong. So now, here's a picture that I cribbed from Eugenio Cocha. Is just the location of the various detectors, both working and anticipated. And so you can see that they're pretty concentrated. I'm going to talk just briefly about the fact that LIGO, Livingston, and Allegro are so very close together. Incidentally, as I go along, as I said yesterday in the class, but for those of you that weren't there, as I go along, if you have a question, please don't even raise your hand. Please just interrupt. This talk was designed to get into 30 minutes so everyone is assured of being able to get out in time for lunch. But I also have, then that means that there's room to answer questions as we go along. So please don't hesitate. Okay. Now it's all stated in that, and I hope to convince you of that. Just as an indication, the cost-effective, my estimate of the amount of money that's been spent in the last 30 years on the Allegro detector is somewhere under $10 million. So you can compare that. Okay, now this is a slide people saw yesterday, except I didn't have the graphics in it. And just for those that were not in the class yesterday, let me point out what this is supposed to illustrate. The the two masses connected by a spring are to represent the fundamental longitudinal mode of a gravity wave detector, of a resonant detector. And let me use, well, my pen is probably better because I can change the length of it. Let me use this as a bar. This is a bar detector. We're going to talk about spherical detectors as we come to the end of the talk, but this is a bar detector. The bar detector is isolated from the outside world, hung, balanced on a wire around the middle. A gravity wave comes in. Gravity wave excites the fundamental, something that will couple to the quadrupole. The gravity wave will couple to the quadrupole modes of the bar. The lowest mode of a bar detector is the fundamental longitudinal mode, one where the length changes, like this. Okay? And so in the bar detectors that we have been using, that all of the groups have been using, the fundamental longitudinal mode in all but one of them is about 912 hertz. And I can say that pretty precisely because we have supplied the bars for all of them, all of the Italian ones as well as ours. And the one that's different is the Australian detector, which is made of niobium rather than aluminum. And it is at about 760 hertz, not all that far away. So, so these two masses then represent this fundamental longitudinal mode. So you can just imagine two masses connected by a spring and vibrating at 912 hertz. Hung on the end of the bar is another mass. And what we arranged to do with our transducer is to, and I'm not going to talk about transducers today at all except to say that they can be improved. We measure the distance between the end of the bar, represented by this mass, and this the small mass transducer. Okay, now these are two coupled oscillators. Because they are two coupled oscillators, energy will they will beat together. This, incidentally, is arranged to be at the same frequency as the fundamental longitudinal mode. And we know then from freshman physics that the amplitude, the little x that we measure here, of the small detector, of the small mass, will be larger than the amplitude with which the big mass is going by this ratio. Australian government has decided that they cannot afford to put any more money than what they are already putting into the effort in Perth. This is where Niobe is. And so the Australians, David Blair and his group, are having a great deal of trouble finding funds to keep Niobe operating. And it is not at all clear that they will be able to do so.
So how much do they need?
Oh, a couple of 100K Australian a year. Helium is more expensive in Australia than it is here. And there's some complicated politics that I don't want to talk about on the web, now I want to try to convince you. I remember I said they were reliable and they had operated for a long period of time. Here is a graph taken off of the IGEC site showing the 5 bar detectors and the length of time that they were on during this 3 years. Now, at this point, we had to shut Allegro down to move it from the building where we had been into a new building. There's both an opportunity and a disaster in that. And I'll mention both of those. But I wanted to show this graph because I wanted to make it clear that the crucial thing, when you cannot find gravity waves with one noisy detector. And so no matter how good your detector is, it is crucial to avoid these blank places here, and you can see the occasional blank places in here. In other words, these things have to be operated at the same time for extensive periods of time. And that is a difficult problem. And I commented to the class yesterday that it is very hard to get over the idea when we've all been building these detectors. You build the detectors and you make it better and better and you get it operating, and the damn thing does not work as well as it should. And you figure out why it isn't working and you say, well, let's shut it down and fix it. Now we knew on our detector operated pretty much continuously from the middle of 1991 until the end of 1994. We knew what was wrong with it. So we shut it down. We told the NSF we were going to shut it down for 3 months, put in a new squid, which was a lot better, and operate it, and then bring it back up into operation. It took us 1.5 years for various things. During all that 1.5 years, then there was no one looking for gravity waves here, and it was not good. It was not good. So you've got to keep them operating for a long period of time, or as long as you can afford. And actually, some of these blank places in here, these were times that we had agreed on that everybody was going to do some calibration or something like that. So this is an article. This is a graph taken from a PhysRev letter that we published a couple years ago. And now I have to apologize again for a change in units. With a resonant bar detector being a relatively narrow-band object, it makes as much sense, and in fact maybe more, instead of talking about little h, strain per root hertz, it makes as much sense to talk about the Fourier component of h at the antenna frequency. And since that's what the Italians wanted to use, and there are more of them than there are of us, that's what we use. And so this is our guess as our upper limit, if you will. Now notice, this is to illustrate a couple points. This is so we're in 1998. We have what, 40 days, 45 days of 1998, and notice how this upper limit. What we're doing is we're trying to run the whole network as a coordinated observatory. And then calculating from that, we didn't see any gravity waves. I want to stress that also. There should be no need to stress that here with this group. But I have, on occasion, given a talk about this, and someone sees something like that, and they say, oh, haven't you found gravity waves? And I told the class yesterday about the mistake that we had made in some of our data analysis, where I had to give an impromptu talk at a GR meeting where word had gotten out that we had seen gravity waves, and we hadn't. And so we have not seen gravity waves. But what we are able to do, operating as a network, then you can see that our upper limit changes by almost an order of magnitude, depending on how many detectors are up or down at a given time. And you can see here some detector was not operating, and then we got a new one operating, and our upper limit dropped by a factor of 2. And now here, a good number of them were offline, and so forth. Here's the article, and here is another expression of upper limits during the 3-year segments of the 3-year time that we were operating. And this is when 2 detectors were operating at the same time. We could get from the 104 days that were looked at, we had 89 days where we had good overlap between Allegro and Auriga. On only 14 of the days were we able to get 3 of them operating, but while the 3 were operating, this is the kind of upper limit you got. Notice, incidentally, this is the rate per year, and this is the Fourier component of the signal at the antenna frequency. And here, lo and behold, we have 4 of them operating. And when you get 4 of them operating, notice what it does to the upper limit you can get. So or to the rate that you can get anyway. Seeing nothing, you can do a Bayesian analysis to go back and say, okay, what was the rate that gravity waves had to be coming in at that time? And so the point that I would hope to leave people with from that graph, and so now I want to stress this, the point I would hope to leave people with is that even if the bar detectors are not as sensitive as the interferometers, for the next number of years, it makes sense to, in my opinion, say, and you are free to disagree, but it makes sense from the physics to keep the bar detectors operating and to coordinate as well as we can between the interferometers, figure out how to coordinate. And as everyone here knows, we did that during this last engineering run to figure out how to combine data, how to coordinate them. Okay.
Bill?
Yes, sir.
I didn't understand from your statement about the future for Niobe. Are they in danger of being shut down?
Yes.
Or not being improved?
No, they're in danger of not having any money,
Eliminated.
The bar will sit there, but it won't do anything if there's no helium to keep it cold. Now, in order to stress the international nature of all of this, I cribbed this off of one of Eugenio Koch's signals. Notice the language that we are using up here, but we're referring to the Allegro detector.
Allegro is an Italian word.
Well, okay. Well, then we're okay. For those that don't know, Allegro's the detector at LSU, and here we see for Allegro, as we were going along, days from 1 January 1997, and we have about a year's data there. You can see how now here, for instance, going along here, I think these were taken every 20 minutes, the average. But you can see, okay, here we were sick, and we did something to fix it. But we did something outside. We didn't warm it up. And the equivalent for you guys would be breaking the vacuum. We just didn't do it. Now, here's a graph that I showed yesterday, and this comes back to your question. This is the noise spectral density from Allegro. This was measured in 1993 before we shut it down to repair it, and we were worse by about 30% when we after we fixed it. And you can see clearly the sensitive areas are here and here, hertz or 2, either place. And basically, for those that weren't in the lecture yesterday, what we did to make this graph came out of Norbert Salomonson's thesis, and what we did to make this graph was we excited that we have a calibrator on the bar. We were able to excite it with white noise. And then, so we had applied a perfectly white excitation to the bar. And then we're able to divide by the ordinary noise. And this is the curve that comes from setting the signal to noise ratio equal to 1.
Why don't you just hit it with a hammer?
Say again?
Why don't you just hit the bar with a hammer?
Because it's way down deep inside.
There's no hammer built in.
There's no hammer built in. Moreover, it would probably be dumb to build a hammer in. Because to figure out a way to put a hammer in, you know, if you're talking about something mechanical or something like that, why you've got a horrendous problem with vibration isolation.
Well, the Leica trick is turn the feedback sign perfectly quick. The feedback loop gives it a whack.
Yeah.
And then look at the ring down.
Yeah.
It's different, I see.
It's different, and I've argued with David Blair for years. This is the way David basically calibrates his antenna. Also, is by Blair uses a different kind of transducer than we do, and in this talk I'm really not talking about transducers. Blair uses a different type, but it's one where he turns it on and off to basically put a force on the bar. And he claims that by doing this, and I think he's convinced me, that he's calibrated so that he knows how big a signal he's put in. Now what we do with our capacitive transducer, our capacitive calibrator, is we also excite the bejesus out of the bar, and we use the calibrator as a transducer. Now you have to, you know, we're many orders of magnitude above where we're operating it here, but we can measure how well the calibrator works as a transducer. And using that and a general knowledge of just a basic 2-port, why you can calculate how much power you put in with no assumptions. With no assumptions. So you can calibrate your calibrator, and then use that to go ahead and make your measurements. And I just philosophically, I'm not saying that your way is wrong, but I said
This way you can measure the amount of energy.
Yeah. And philosophically, I just like it better that I know that I have put in this many ergs. Okay. Now, for the class yesterday, this is the correct data. All right. I put this graph in here. I would hope that you see the numbers. This is from Evan Moselli's thesis. And this is where you can find it on the Los Alamos site. We did because we were able to keep the bar operating for an extended period of time, we were able to average signals for a long, we were able to make a bunch of averages of signals taken over a relatively wide time frame. This is, as I recall, 28 hours, and then we have a bunch of 28-hour segments that we then averaged. And by doing that, now we changed units again. We're down to little h, but this is the numbers 3, times 10 to the minus 23rd. And this is, we were looking for bright lines. And this is, I chose the one here in the galactic center. We looked in the galactic center, we looked in the, and we chose the direction of 47 Tuc, a globular cluster, which has a whole bunch of millisecond pulsars in it. And when we had analyzed the data wrong for the first time and the word got out, we had a couple of bright lines in here. Not very big, 2.8, 3 sigma, something like that. But we didn't, we found the mistake. It took us a year to find it, but we found the mistake. And there aren't any bright lines here now. So we could not see any CW sources at that level, something which did not change its frequency for the months that we averaged the data. I should also make a point. Let me go back here. Notice, everybody, that right here, there's a glitch here in this line. That's right at 900 hertz. 900 hertz is the 15th harmonic of 60 cycles. We have been operating since 1991, and we've never been able to make that damn thing go away until 6 weeks ago, when we found that we had a longitude. And what this was, it turns out, was a little bit of 60 cycles leaking into the calibrator. And so actually putting a signal on the bar. And in the run with, where we were trying to run with LIGO and get our signal, get our detector back operating again, we found that the longitudinal choke on the line that was going to the calibrator was for one reason or another, was on the ground side rather than on the hot side when we just took the plug out, turned it around, and the 60 cycles went away. Well, you know, once you find them, they are. The trouble is finding them. And see, we only have one feedback loop. You guys have 28, I think, was what I calculated. Okay, you remember the Allegro curve? Okay, here's a curve taken from Auriga, operating at 200 millikelvin, and hopefully it can get down to 100. But notice they've improved the noise level substantially. Their little h here is down to a couple times 10 to the minus 19. So things can be made better. We know what to do. And there's another thing. In this paper, the group at Trento and Legnaro have figured out a way to make a better squid amplifier. Better than what and it turns out a cheap way to do it. So the noise temperature of this amplifier is better than what we've been using by probably an order of magnitude. So we have some real hope on improving things.
Well, how close to the quantum limit is that amplifier?
I don't know. I don't remember. I just didn't work it out. And we know how to make the detector more broadband. And this is just a MATLAB simulation of what we think Allegro will do with a transducer that we hope to put on it within the next few weeks, that from the University of Maryland. Theirs has got much closer coupling, much tighter coupling, much higher coupling, because the spaces in the transducer are much smaller. It remains yet to be seen whether it will work in a real on a real detector where you have to put it in, you've got dust and all sorts of other stuff in. And, but we...
So what's the time scale to try to do this?
Well, PAC has it, the bar is, the detector is open. Now, we warmed it up, we're open. They are doing one more test on it, and then they are supposed to bring it down and put it on Allegro in, you know, in the next few weeks, which means it'll be done over the summer. We cannot, or I have told everybody that we cannot possibly make a run to try to run in conjunction with the next engineering run. There's no way that we are going to be able to work that rapidly and get this all together. But certainly we can by the end of the year. Now, this is what I wanted the sound for. This is kind of fun if it works. It didn't work in Albuquerque, but let's see if it works here. What I'm trying to illustrate, and this is something everybody here knows, but the people in Albuquerque didn't necessarily. I had a, so this is just something I genned up with. I was going to try to actually optimally filter this. So I put on a, just to listen to what you get from a burst like this. This is 500 hertz. Okay, and I think I have 1, 2, 3, 4, 5, 6, 7 cycles of it. And the question is, let's see. There. Hear it? Okay, well, we can do it again. Okay, so take that as a signal. All right. Now, so what I'm going to put on top of that is just plain old ordinary Gaussian noise. All right, there you go. Now you're not going to hear that because I didn't put anything on it. But now here we get the signal and the noise. Okay, notice you don't see anything on the graph. You don't see anything on the power spectrum. Now, do we have any musicians here? One of my musician friends, and I think maybe I, can't. Did you hear it? Yeah. Mm-hmm. Okay, try it. You want to listen again. Now, what I've done is I have this coming exact, this is a 4-second segment, and it comes exactly in the middle. You don't see anything here. It's at 500 hertz. Notice you've got all sorts of things sticking up that you might think was a signal, but it isn't. Okay? Now, let's take 5 detectors. You would be tempted to say, and you would probably be right, that maybe there's a signal there. However, you say, is that a signal? And the answer is no, it isn't. Notice the frequency that it's at. It's not at 500 hertz. Nothing in the power spectrum. But when you add them all together coherently, you can hear it. No, there's no question but that it's there. And so the purpose of this was to, and now this is stuff that everybody here knows, and I just want to point out that I didn't put the graph in, but Albert and Sam Finn were primarily the people responsible for this last over beer, and where were we at MIT? They came up with the idea of could we rotate Allegro, and so could we make it parallel or anti-parallel or whatever to the arms at LIGO Livingston? And the answer is that we can. And because we had to move it, because they built a new building over our lab, we did, and we have it. We proved during this last run that Allegro was, it was possible to rotate it. Not only was it possible to rotate it, it was possible to rotate it cold. And as we rotated it, we found that it would work perfectly. It worked perfectly well within half an hour of doing the rotation. So we can look for signals, the difference in signals between being aligned with one of the LIGO arms or not, rather than being perpendicular to that great circle. And now I just want to spend a moment or two saying something that is being worked on. Here are 3 projects going on in the world. Sfera in Rome, Mini-Grail in the Netherlands, and the Schenberg experiment with Odilio Aguiar in Brazil.
Where is the name Schenberg?
Famous Brazilian physicist. Here is from the Brazilian group. Here is they're in the process of. Oops. I messed the whole thing up here. Is it still working? Yeah. Okay. They're making a sphere here. Now you will notice that the sphere, not yet a sphere, you will notice that it looks a little weird if it's aluminum, and the answer is that it isn't aluminum. They're using a copper aluminum material that they can get made in Brazil. This is Odilio Aguiar. Some of you know him. Many of you do not know Giorgio Frassati, who has quite a name in low temperature physics. He has his own company that makes helium-3, helium-4 dilution refrigerators, and got interested in doing gravity waves. The Brazilians have money. They built a whole, here's the building that they built. And they are, well, as you saw from the previous picture, they're actively working on it. Here is a website for you, which is actually quite a nice one. This is the support for the sphere as that Giorgio Frassati intends to use. The 3 groups are working together. Now, the advantage to a sphere is that a sphere will detect gravitational waves coming from any direction. What Warren Johnson and Steve Merkowitz showed with their CaJAGWR experiment was that it was possible to put 6 transducers on in their case, they used a soccer ball shaped instrument, we called it a CaJAGWR, truncated icosahedral gravity wave antenna. And they used, and they showed that they could hit it with a hammer and get signals out from it and tell exactly where the hammer had struck just from how the transducer was excited. And so here is Eugenio Coccia from the Italian group. There is the sphere made in Brazil, and of this alloy, which Frassati has measured, says that its Q will be quite high. That means its losses will be low. That means the noise will be low. And I want you to notice it's mounted here. There's a hole all the way through it, and it is mounted at the center of mass, or just slightly above the center of mass, so that any vibration that couples in will not excite the quadrupole moments. If it's hung right from the center of mass, why, it should not be excitable. That remains to be seen. The spherical detector, whoops. This is a curve off of Frazzati's website. Again, this is something that he gives thanks to David Shoemaker for the graph for advanced LIGO, and then this shows the goals, the things that they're looking for. They're even talking about a 2-meter beryllium sphere.
Frequency?
Hmm?
The frequency?
The frequency, I'll notice it's 3,300 hertz.
Now, if you have a sphere, and it derives from the center of mass with a noisy bar or hang or
Yeah, yeah.
I think the excitation that will, if the bar is noisy, it will excite the
Sure.
sphere, because you cannot hang it right from the center of mass.
Exactly so. You're right. So it is like we have all found out, and like when I talked to the class yesterday, the reason that Allegro is as good as it is because of the vibration isolation that we've gotten. And the problems that you all are having now are, we're finding, you build a better instrument, and all of a sudden you find that things that you had not anticipated come in, and we've got vibration isolation problems. And of course, your vibration isolation problems are much more difficult than ours. And the sphere has a much more difficult vibration isolation problem than the bar detector, because the sphere has to have transducers on it that will be sensitive to motion up and down. So so conceivably, even though the bar wasn't excited, if you shake a sphere up and down like this, you could get its transducers excited.
You'll primarily excite the dipole noise.
Yeah.
Well, there will be a great suppression of the excitation of the quadrupole noise.
Yeah. Okay, well, I'm done. I think that was the last one. Let's see. Well, we should put that up. But basically, I'm finished.
I've got 30 seconds more.
Okay. And so I want to stress this, and the other things are the lessons that I would hope that you all will carry away. Okay, thank you.
Thank you.
There was a talk about 1 year ago about sawing off a piece of Nautilus to bring it at higher frequency tuned on 87A. Anything happened?
Not to my knowledge. They're still talking about it, but I don't believe they've done it. And at least I don't know about it.
What I heard the last time is that they oversawed a little bit, so they moved the first peak off, and they had to saw another little bit off to put the second peak on resonance. But that is what I heard the last time.
Oh, okay. Well, then you know more than I do.
I hope to know more. We'll ask her.
Yeah.
We'll ask Eugenia.
Yeah.
Nancy.
So the group in the Netherlands has had trouble getting funding for what they wanted to do. Do they have funding to move forward with mini grail?
I believe yes, they do.
Wanted to build something.
Yeah, I don't know whether they have government funding. I think Frazzati may just be funding it from his company. His company makes helium-3, helium-4 dilution refrigerators. It's been quite successful. And it's his own. He doesn't need to answer to anybody. And it is also relatively inexpensive for him at Leiden to build scientific apparatus, because Leiden is a long time. The university has a long-time school for training technicians. And so these people are giving him a lot of help. He's got alliances with other Netherlands universities. There's one that specializes in making different kind of squids than we are using. And so I think they're going to make it go. They were having trouble early on. A bunch of nuclear physics guys got into it and wanted to turn it into some sort of giant project. And it just, that got canceled. And well, that was the original Grail project. That was when we were talking about a 3-meter sphere, and which we couldn't get money for either. But it makes sense to me, anyway, to try these things, run them together, run them with LIGO. I mean, you guys may see something at 3 kilohertz. You know, who knows? And it would make a lot of sense if they saw something too.
At 6 kilohertz, LIGO is already pretty dominated by short noise.
Sure. Okay. So what? Yeah. Yeah, you're not as good as you would be, but you're better than not looking. Yeah. Yeah.
What sources do you expect?
Well, as we said yesterday, could be a ring down of a black hole, could be some excitation of a neutron star. You know, it's some kind of condensed object, clearly.
Do you expect LIGO to have enough manpower and computer time to do the search over all these bands, or would you suggest that we would look especially at the frequency where your detectors work as well, so that we can have some correlation? Well,
it would certainly make sense with our detector, when we're running our detector, looking for a correlated signal between our detector and LIGO. It certainly makes sense to look there in the LIGO data, and you know, and a group in the LSC is actively looking at that.
But Bill, I mean, depending on the frequency time characteristic of the signal, I mean, it doesn't have to have exactly the same frequency overlap as long as it has spectral content approximately in the same.
Exactly so. Exactly so. And so, you know, we get blinded by this search for most sensitivity and all. And yes, we want to make them as sensitive as we can. But once we get them working, why, you know, let's operate them and get what we can out of it. And there'll be, you know, if it makes sense to look at 3 kilohertz, there'll be people will find the computer power to look in that data if there's something there to be done. That you know, the University of Wisconsin and they have their own stuff. With LSU will have its own big Beowulf cluster that isn't even part of any of the computing facilities that we've talked about.
So if LIGO data will be made available for you, you can just...
Sure.
And I guess it will.
Well, I mean, it eventually it will have to be. Yeah.
Any other questions? Well, thank you very much, Bill.
Okay.